When we first met, soon to be divorced. There we go. All right, we're live. So, Kinetic Molecular Theory, Chapter 9. So, Chapter 9 means we are starting to talk about the gas laws. So, Kinetic Molecular Theory. These are the postulates of the theory. So, basically, people were studying the behaviors of gases. Not just air, but any gas. And they wanted to understand why they did what they did. So, they just made lots and lots of observations. They eventually built up to the gas laws, and that brought us to, in the end, kinetic molecular theory. So I'm going to go ahead and start with the theory. Then we can use that to explain the gas laws, because that's what the theory is for. So the postulates of kinetic molecular theory are that gases are composed of tiny particles in constant random motion. Yeah, obviously. Gases are composed of atoms or molecules, and they are constantly moving. Now, the volume of the particles is negligible compared to the total volume of the gas. That is to say that the space between the gas molecules or atoms is much, much bigger than the space occupied by the atoms or molecules themselves. Or they're insignificant. For all practical purposes, we say that the particles themselves don't occupy any volume. Next up, we say that the gas particles do not interact except through collisions. They bounce off one another, but there's no attraction, there's no repulsion, they bounce. It's like a really, really big, infinitely large game of pool. Click, clack. Now, the collisions between the particles and with the wall of the whatever container the gas is contained in are perfectly elastic. So elastic means that no energy is lost. The container or the particles, well, let me describe an inelastic collision. A car crash is an inelastic collision. Some of the energy of the car is transformed into crumpling of the car. So you see a NASCAR crash. Those cars are designed to crumple a heck of a lot and fly to pieces so that as much kinetic energy as possible is transformed into the collapse of the car. That way, it sheds kinetic energy. It slows down really, really fast, and it gives the driver a much greater chance of surviving. Whereas inside the gas, they're saying it's a perfectly elastic collision. So all of the kinetic energy of the gas molecules remains as kinetic energy. They don't lose any to any other sort of motion. And finally, the average kinetic energy of the particles is proportional to temperature. Now, this is what temperature is. It's a measure of that average kinetic energy. That's not a problem. But what this means is that higher temperature means the particles are moving faster on average. Okay? Some particles will be moving faster at some times, some particles will be moving slower, but temperature tells us the average. So some postulates are better than others. First up, the terrible postulate, the one that says particles don't interact. They do interact. Obviously, they interact. This is why we have chemical reactions. This is why gases turn into liquids. It's because there are these interactions. And at low temperatures, the particles are moving slowly, so they can interact even more. So what that's saying is that at high temperatures, this postulate is okay. At low temperatures, the lower the temperature, the worse this postulate gets. The particles interact more and more and more, and eventually the gas turns into a liquid. Now, the not so terrible postulate is the one that says particles don't have volume. They do have volume. They're made of mass. They take up space. However, particles are really, really small. Atoms and molecules incredibly tiny. And the space between gas molecules usually is enormously bigger than the space taken up by the particles themselves. However, at high pressure, when the particles are really packed together, it becomes significant. You do have to start acknowledging the fact that gas molecules, gas atoms, take up space. So these two, oopsie, come on, there we go. So these two things, these postulates, sometimes they apply, sometimes they don't. So this one tells us that at low temperatures, these postulates start to break down because the particles do interact. And this one says that at high pressure, these particles start, the space occupied by the gas molecules or atoms starts to become significant. Meaning, conversely, at high temperatures, when the particles are moving really fast, at high temperatures, they don't have time to interact, so this postulate holds. And at low pressures, when the particles are really far apart, this postulate it holds. The particles, we can ignore the volume of the particles much better at low pressures. So this is what gives us the terms ideal versus real gas. An ideal gas is one that conforms well to the postulates of kinetic molecular theory. An ideal gas is easy to model. It's easy to understand. So this final online lab, Lab 13, where you're playing around with that simulator, that is modeling an ideal gas. Just particles moving in perfectly straight lines, not interacting with each other except to bounce off one another. That is an ideal gas. A real gas doesn't conform well to kinetic molecular theory. It violates those two postulates, the one that says they don't interact and that they don't take up space. So, ideal conditions are high temperature and low pressure. Once you start getting to low pressure, once you start getting to low temperature or high pressure, then you're starting to look at a real gas, as in one that has different conditions, different, I can't think of the word, different properties. There we go. It has different properties than you expect, different properties that we can measure. Speaking of which, there are 4 properties that we tend to measure for a gas. And now I'm going to spend some time talking about gas pressure. Now, I already introduced pressure when we were talking about work back in Chapter 8. But pressure is a really big deal for gases. So I'm going to go ahead and go over it some more. Go over it again, really. Now, pressure, remember, is force over area. So for a gas, it exerts pressure when the particles of the gas collide with something. So if you're talking about a gas inside of a container, the gas is able to exert force by colliding with the walls of those containers. Now, each collision is incredibly small because the particles of the gas are incredibly small. However, there's a lot of particles. There's skajillions of these guys. So lots and lots and lots of collisions means that force can build up to, something appreciable. Now, the area of the gas is the area of the walls of the container. Okay, so a small container has small area, big container has big area because just more wall. That means that the pressure exerted by a gas inside of a container is the force of all those collisions divided by the area of the walls. Now, the reason I'm making a point to bring this up is because later on, when we're talking about the various gas laws, it will be helpful to have this sort of physical explanation for why pressure changes in response to other properties of the gas being changed. So, if we want to change the pressure of a gas, we either have to change the force exerted by the particles, or we change the area of the inside of the container. So, one way to increase pressure is to increase the force of each individual collision. Okay, make the particles move faster. Another way is to increase the number of collisions. Okay, if there's more collisions, then the total pressure will increase. That means increasing the amount of gas. The other way to increase pressure is to decrease the area. Remember, come on. There we go. Remember, pressure is force over area. So if you decrease area, you're dividing by a smaller number, so pressure gets bigger. So decreasing area means decreasing the volume of the container. There's less wall. If there's less wall, if there's less volume, then the pressure exerted by the gas will increase. So, to remind you, the SI units of pressure are the Pascal, named after Blaise Pascal, a French scientist and mathematician. 1 Pascal is 1 Newton per square meter, but of course a Pascal is an incredibly small unit of pressure. So we also use the atmosphere, 101,325 pascals, or 101.325 kilopascals. We also use the bar, which is 100,000 pascals, or 10 to the 5th pascals. And then we also have the millimeter of mercury, or torr, where the millimeter of mercury is equal to the torr, and 1 atmosphere is 760 of those. All right. So this is the picture I sketched out horribly of a manometer, or barometer, a device for measuring pressure. So you have a tub of mercury, and you have a tube of mercury sealed at one end, open at the other. The open end is, in the pool of mercury. Gravity pulls the mercury down, but it stops because you also have atmospheric pressure pushing on the surface of the tub of mercury. That pressure is uniformly distributed throughout the fluid. So it's also pushing up on the mercury inside the tube. So however hard the atmosphere is pushing on the mercury, that determines the height of the mercury inside the tube. And 1 atmosphere of pressure will keep the mercury elevated to a height of 760 millimeters. Less pressure, less height, more pressure, more height. Named for Torricelli, an Italian scientist. Okay. So, because they're far more likely to ask you to do these conversions in this here semester, let's go ahead and practice doing these conversions now. You'll notice that we have 2 separate portions of this chart. So here we're going to be converting from pascals to atmospheres, then to torr. Here we have atmospheres, convert that to pascals, and then to torr. And here we have torrs, and then we have the other side of the chart where we do the exact same thing. So go ahead, pause the doohickey, and try and do these conversions yourself, and then come back. All right, welcome back. We're going to go ahead and walk through these conversions ourselves now. So, 98,230 pascals converted to atmospheres and torr. So, 98,230 pascals times where you're going to goes on top. So we're converting 2 atmospheres from pascals. There's 101,325 pascals in 1 atmosphere. So 98,230 divided by 101,325 means that is 0.969. We have 4 sig figs there. 9694 atmospheres. And then we can convert directly between pascals and torr. It's not particularly challenging. 98,230 pascals times torr, or millimeters mercury, and pascals. So 760 torr is the same as 1 atmosphere, so it's the same as 101,325 pascals. You could come up with a more direct measurement, but or more direct conversion factor, but who cares? It's 98,230 times 760 divided by 101,325. Whoa, what the heck just happened there? 98,230 times 760. Okay, I see. Divided by 101,325. All right. So 98 pascals is equal to 736.8 torr. Now, next up, we have 2.33911 atmospheres. So there are 101,325 pascals in an atmosphere. So 2.3911 times 101,325 is 20. 2.3911 times 101,325. Love it. 101,325. Come on. There we go. 242,280 pascals. Or 760 torr per atmosphere. 2.3911. Gosh darn it. 2.3911 times 760 is 1,817.2 torr. And now at the bottom of the chart we have 873.45 millimeters of mercury. Might as well get used to seeing that as well. So there's one atmosphere for every 760 millimeters of mercury. 873.45 divided by 760. 1.1493 atmospheres. And then there are 101,325 pascals per 760 millimeters of mercury. So we'll just go ahead and multiply this number by 325. That means that there are 116,450 pascals in 873.45 millimeters of mercury. Coming over to the other side of the chart, we have 4 pascals, and we have 43712 atmospheres, and 659.129 millimeters of mercury. All right, so 1 atmosphere for every 101,325 pascals means 1123214. That's a lot. Divided by 101,325, it's going to be about 10 atmospheres. 11.0. 1, 2, 3, 4, 5, 6, 7 sig figs. 11.0. That's 38526 atmospheres. 760 torr for every 101,325. That's a 1 is equal to 8424.798 torr. 8,424. That's a lot. All right, and now atmospheres to pascals. We're going to multiply by 101,325 pascals per atmosphere. 0.43712 times 101,325. 44,291 pascals times 760 torr per atmosphere. (332.21 atmospheres. So these numbers, by the way, 101,325 and 760, those are both exact by definition. So they have infinite numbers as sig figs. So our whatchamacallits, our significant figures are limited by whatever number we start with here. And now there's 1 atmosphere in every 760 millimeters of mercury. So 659.129 divided by 760, a little bit less than 1, maybe 0.8. Oh, yeah. 0.867275 millimeters of mercury. And then times 101,325 pascals for every 760 millimeters of mercury means that it is 87,876.6 pascals. All right. So those conversions aren't excessively difficult. Kind of annoying, but ripe for a multiple choice problem. You never know. All right, so that is the introduction to kinetic molecular theory, which just states that gases are made of moving particles that only interact through collisions, and that they move faster. And then we have pressure, which is force divided by area. The force is exerted by particles colliding with the walls of the container, and then the area is the measure of the area of the walls of the container. Okay, so we're going to be using kinetic molecular theory and this definition of pressure, this understanding of pressure, to explain the gas laws. Okay, so we come here, we see our gas laws, and then we have our ideal gas law. So those are the things that we will cover next. But not tonight. I'm feeling lazy tonight. I'm going to go ahead and call it for the evening. I will see you tomorrow.